Then we start with the first presentation from Matthias Hofmann from the Brenner Base Tunnel, construction lots for railway equipment at the Brenner Base Tunnel. Please.
So, good morning, everybody. It's a pleasure to be here and to have the ability to present the Brenner Base Tunnel project. And the presentation is divided in 3 sections, so I will start with the introduction of the Brenner Base Tunnel project a little bit more in detail because it was not presented yet very often in such a conference. Then I will go ahead with the railway equipment phase, which is about to start or started already, and then about the track systems planned at the BBT. So, as an introduction, I will show an excerpt of a video of the BBT, which shows a good introduction to the project in general. It's okay.
Engineers, planners, geologists, miners, and many other professionals work constantly, tirelessly, tenaciously, with precision and skill, 24 hours a day, 7 days a week, on one of the cross-border projects of the century, the Brenner Base Tunnel. All the different groups working on the construction sites and in the offices are like gears that mesh to drive this infrastructure project forward. Implementation takes place step by step, like the steady ticking of clockwork. The Brenner Base Tunnel is one of the largest infrastructure projects in Europe, as well as the longest underground railway connection worldwide. A goal Austria and Italy are working towards together is a project that will unite Europe. Once the tunnel goes into operation, the travel time for passenger and goods trains between Innsbruck and Fortezza will be significantly reduced. Travel time for passenger trains will be cut from 80 to 25 minutes. North and south of the Brenner Pass, this will be a significant improvement for residents and travelers. If you want to get past a mountain, there are 2 ways to get to the other side. Either by traveling over it with many steep curves uphill and downhill, or going straight through it underground. A lot of people are working on the Brenner Base Tunnel to build the direct underground railway connection between Innsbruck and Fortezza. A railway tunnel at the base of the Alps, offering the advantages of a flat railway over a total length of 64 kilometers. The Brenner Base Tunnel comprises more than 220 kilometers of tunnel tubes. 2 main tunnels for the tracks with a diameter of about 8 meters and a cross passage every 333 meters. Between those tunnels and 12 meters below is a 3rd tunnel, the exploratory tunnel, which is 6 meters in diameter. This is driven before the others to understand the nature of the rock mass and to find out exactly what kind of rock to expect. Once the Brenner Base Tunnel has become operational, this tunnel can house technical equipment and be used to carry out maintenance work. The 4 lateral access tunnels in Mullis, in Steinach am Brenner, in the Arental Valley, and in Ampass are necessary to advance deep into the mountain and excavate the tunnel system from there on several construction sites simultaneously.
It's available on the YouTube channel, so please feel free to watch it in full length. So, why is the BBT built? Here is a sketch for the traffic road between Munich and Verona, and I will play the intention for the diagram here below. On the left side, there is the traffic going over the Brenner Pass at the moment, which is roughly 150 or 160 trains per day. Mainly the green bar is for the freight trains. And the expectation is that in several years, so 1 or 2 decades, when the Brenner base tunnel is finished, this will be ×3, so there will be roughly 400 trains per day over the Brenner, of which 300 are freight trains. So that is the need of the Brenner base tunnel, and for the whole concept of Europe, the Brenner base tunnel is part of one of the 9 Trans-T networks, the corridors, which the Brenner base tunnel is part of the ScanMed corridor, which goes from the very north of Europe down to the south of Italy. And this connects 7 countries, has a length of approximately 9,400 kilometers, and connects 110 million people. On the right side, you see again a sketch from Munich to Verona, where the Brenner base tunnel is a centerpiece, and the special nature of the Brenner base tunnel that it's a cross-border project, which means that I have 2 concepts, 2 nations, and have to sum it up in one project, let's say. So the Brenner base tunnel, in principle, we talked before, is a blueprint of the Gotthard base tunnel because it was built before, and there it was a good base for copying. But there's one important difference, which is this exploratory tunnel below. And the name is not totally correct. It was for exploration at the beginning, it was for drainage of water at the beginning, concepted, but now it will be used heavily for the equipment phase and for the operational phase. For that, there were shafts built every third cross passage, so every 1,000 meters, you have the ability to go from the exploratory tunnel during operation of the trains up to the cross passages where a lot of equipment will be placed as well as near the exploratory tunnel, so you can do a lot of maintenance work 24/7. So here again a sketch of the whole system, Innsbruck on the left side, Fodessa on the right side, and the whole system, as shown in the video, has a total length of 230 kilometers. Of all this main tunnel, exploratory tunnel, access tunnels, and so on. And important is also the link to this existing bypass tunnel, the Verbindungstunnel Innsbruck, Umfahrungstunnel Innsbruck. And with this connection, so from Innsbruck to Fodessa, the length is 55 kilometers, which would be a little bit less than the Gotthard base tunnel. So we made this connection to the existing tunnel, so it's 64 kilometers, and so it's the longest underground railway connection in the world. One word to the, at the moment, ongoing civil engineering works, civil construction works. This is a plan view, a schematic plan view. This large project is divided in many small pieces for excavation, and the different colors show the different construction lots. A lot of them are completed, but 3 of them are already still in progress and will last for the next 2 or 3 years. So, to sum up, there are in total 230 kilometers to be excavated, 90% are already excavated, so some 25 kilometers are left to be excavated, which will take place roughly in 1 year or a little bit more probably. And there was a historic milestone some 2 months ago where the first breakthrough in this exploratory tunnel between Austria and Italy took place. This was very symbolic because it's the first underground connection between Austria and Italy. And it was celebrated accordingly with a lot of prominence. You see in the middle the Chancellors of Italy and Austria, Meloni and Stocker. The construction of this exploratory tunnel took 17 years in total. So now coming to the railway equipment phase. Some basic numbers. The design speed for passenger trains is 250 kilometers per hour. Whereas for the freight trains is 160 kilometers per hour. The train length is designed to be 740 meters, and the system is deployed with the ECTS level 2. On the right-hand side, you see one of the consequences having a cross-border project. There are all these different space profiles, let's say, plotted. There's one from the ÖBB, there's one from the RFI. There's one from DSI, and the one we used is then the sum of all. This is one of the compromises we have to do if it's cross-border nature. Another compromise requires signaling. Usually you would operate it from one side, the whole tunnel construction. It was a long discussion. It was decided to, here is the border between Austria and Italy, and it was decided that from the Austrian side, from Innsbruck, the Austrian part will be operated. In blue is the new Brenner Base Tunnel, in gray or black below is the existing line over the Brenner Pass. And in principle, the same goes for Italy, that the two tracks are operated from Verona. Another lengthy discussion was about the traction power system. And finally, again, a thing which is not logical at first sight. There will be a separation of the track power systems. And again, in Austria, here in green on the left side, there will be the standard traction power system from ÖBB, which is 15 kilovolts and 16.7 hertz. Whereas on the right side, here in red, there will be the power traction system with 25 kilovolts and 50 hertz, which means there's a power-free section underground, some 1.5 kilometers below ground. And there are other railway equipment issues. I won't go into detail because now in future we will focus to the SLAB track in the following. Before that, a quick outline on the time schedule. A project like this, similar to the Gotthard Base Tunnel, lasts roughly 20, 25, 30 years. In our case, it started 2004, 2005 with the authorization phase. There, the civil works as well as the railway equipment works were first designed and given to the official bodies and approved. Then the focus was on the civil engineering construction for the next, from 2008 on, where the approval was here. And now we are here in the middle somewhere, where in parallel last year the design update or optimization of the design of the railway equipment took place. Here we have a known contractor. It's an ALGA with Italfer. It's Italfer and ELF and some design companies in there, other ones. And they have the goal to update the railway equipment design. And one of the important updates is, as I told before, that the exploratory tunnel will be used as a service tunnel in future, meaning that a lot of, or as much works as possible will take place with the use of the exploratory tunnel or a service tunnel. And this will, we hope that will have a great benefit on the availability of the track, of the railway system. Then the plan is next year or the year after to make the build tenders for the railway equipment phase, then the contract make the tendering. And in 2027, 2028, the design construction should start for the railway equipment, and the works of the railway equipment should start something around 2028. And the, let's say, motivated goal is to finish this phase in 2031, so in 3 years, because it's planned to go in operation in 2032, which is quite challenging, let's say. So, let's come to the track system in the BBT. So we have all kinds of track systems in there. The main track system will be the SLAB tracks, and a part of which, or a certain area will be with a mass spring system built. But also we have ballastic track systems, and so we do have transition zones between these systems. Regarding the tracks, the SLAB track system, there's the principal requirement that it must fulfill the requirements of Austria, of Italy, as well as the international standards, which mainly is the TSI. And in the first phase, in 2004, 2008, it was decided that there will be precast slabs that have to be used, laying on the base layer and possibly with a separating layer between them, like we heard yesterday some examples. The width and the thickness are standard with roughly 2.5 meters and 20 centimeters height, respectively. And this is, as said, typically the systems which are used widely in Austria and in Italy at the moment. Regarding the rail itself, it has to fulfill the typical specific Eurocodes, and the standard track, of course, is 1.4 meters roughly. Then, okay, this is a typical cross-section, nothing special. We see here the case of a drill and blast tunnel, but we have also several kilometers of TBM drives with tubings, but the situation at the base is the same. Yeah, and here an example for how it can look like with a blade system. And there are also parts near the portal where there is a low overburden and some villages and people living above. And especially in Austria, due to this existing tunnel, this Umfahrungstunnel Innsbruck, we know that there is a vibration communication to the houses. So there will be a mass spring system as well, or there will be a mass spring system added to avoid the mitigation of these vibrations. And finally, there will be ballasted tracks areas, especially also near the portals where the existing tracks will be go inside the tunnel for some meters with ballasted track system. I will come to it in a minute. And so, as there are different systems, there are transitions between the systems. And I saw that there will be a presentation afterwards, so I don't go into detail. Only maybe that this transition has to be in several steps, and the differential deflection between the steps must not exceed 0.5 millimeters. So where are these different track systems located? Here we start in Innsbruck. It's a schematic view. Here on the left is the main station of Innsbruck, the existing one. And there will be the connection to the tunneling system with ballasted tracks. Here's the portal roughly. And as you see, the first meters in the tunnel are also with this in black, this ballasted track system. As well, here you have the connection tunnel, and this is still is already in operation since 1990 roughly, and has a ballasted track system. It's for freight trains, and the connection here will also be the first meters with ballasted track. Here, this is the reason is because this is a very difficult geological structure. The slope is not stable, is the wrong word. It's a creeping slope. So there's the possibility that the whole tunnel can deform some centimeters up to decimeters. And so with the ballasted track, we have the possibility to readjust the rails. Next to them, going direction south, there are slab track systems with mass spring systems. There are different kinds of spring systems foreseen. These are some kilometers, is this connection to the existing tunnel as well as the first kilometers in the BBT. And then from here on, the main part until the southern portal will be in slab track system. And now going to the other side, to Fortessa, there comes the trains, the main tunnels with the slab track system. Here is an interesting area. This is the crossing of the tunnel below the Isako River. So there will be, this was a huge, interesting construction lot, and this will be deployed with a spring system. And at the end, again, the connection to the existing lines will be with ballasted tracks system. So to sum up the numbers, which are probably most interesting for you, is there will be in total roughly 100 kilometers of slab track system. Additionally, something between 20 or 30 kilometers with mass spring system added. And I wrote here 5 kilometers. I don't know. It's depending on the measurements. Probably it's less than 5 kilometers. But some areas, as I said at the beginning, at the end, and will be with ballasted tracks, so we have to pay attention to the transition zones as well. With that numbers, I come to the end of my presentation. If you would like further information for the introduction, please go to our website. There are a lot of information there. And with that, I thank you very much for your attention.
Thank you, Matthias. It was a very interesting presentation. Our next presentation comes from Turkey. Professor Ömür Akbayır, please. You will present us, hello, for the structure analysis and construction of a cut and cover tunnel slab track. Please.
Good morning, everyone. My name is Ömür Akbayır, and I am from Eskişehir Technical University. Together with my colleague, Ceylan, from Turkish Railways, we prepared this paper titled Structural Analysis and Construction of a Cut and Cover Tunnel System Track, the Gaziray Experience. We are here representing the Turkish Railway Association, Engineering Association, and our groups consist of 6 members attending this conference. It is a great pleasure for us to share our work and experiences with you today. In this presentation, I will talk about the Gaziray project, one of the most important railway investments in Turkey. The project includes a 4.8 kilometers cut and cover tunnel, where a slab track system was designed and constructed. Our main goal was to analyze the structural behavior of this system and explain the construction process step by step. The Gaziray project is a good example that shows how engineering design, construction management, and practical solutions come together in a real railway project. We believe our experience will be helpful for similar track projects in the future. Now, let's start with the brief overview of the project. The Gaziray project is located in Gaziantep, Turkey. You can see its location on the map. It was developed by Turkish State Railways and the Gaziantep Metropolitan Municipality. The total road length is 25 kilometers, and 4.8 kilometers of this road is built as a cut and cover tunnel. Here are some quick technical details about the tunnel. This tunnel passed through residential areas, so the cut and cover method was chosen to reduce noise and improve safety. Inside the tunnel, we used a slab track system instead of ballasted track. This system is more rigid, needs less maintenance, and offers better long-term reinforcement. For the structural analysis, we use SAP 2000 software and consider UIC LM71. For materials, we use high-strength C30 concrete and S420 reinforcement steel. The project has 4 main steps. Now let's start with the step 1, building solid foundation. Our first priority was the tunnel stability. As you can see in the photo, this was a huge operation. We constructed 7 bore piles ranging from 14 to 21 meters. Moving on to step 2, the cut and cover structure. We perform a massive excavation of 1.8 million cubic meters. Then, as you see in this photo, precast girders were installed to cover the tunnel. Now, step 3, reinforcement and concrete. We placed double row S420 steel reinforcement. Plastic spacers were used to protect the protect the signaling system. We maintain a surface tolerance of plus or minus only 2 millimeters. This precision is essential for a high-quality slab track. Finally, step 4, rail fastening and final assembly. 60 E1 rails were fastened directly to the concrete slab using the elastomeric fastening system. This system reduces vibration and allows thermal expansion. As you see in the photo, we integrated 4 large switches or turnouts directly into the concrete slab. So, we built this rigid track. This creates a new question. What about the vibration? Remember, we are right next to homes and schools. We also made a vibration analysis to protect the nearby buildings and improve passenger comfort. In critical zones, a mass spring system to keep vibration level was installed to keep vibration levels under control. The black vibration absorbing mass you see in the photo were placed under concrete slab. In short, the Gaziray project combines structural design, practical construction methods, and vibration solution in a single modern railway system. Thank you.
Thank you very much. An interesting aspect. Then the next presentation is modernization of the Tauern Tunnel, partial renewing from Thomas Lercher. Hello. Yeah.
It should work, yes. Good morning, ladies and gentlemen, from my side. It's a pleasure to talk in front of such an expert and experienced audience. It's a great pleasure to be here. We all share a passion for the topic of railway. We share a passion for the topic slab track. And I will explain you the project of the Tauern Tunnel. We have already heard many highly interesting presentations with many theoretical parts, with material behaviors, with introductions of slab track systems, and even life cycle costs. But now I would like to invite you to a journey to the construction site. Maybe you remember back at the university or in school when the professor entered and invited you to visit a construction site. Everybody was really happy, and I hope I can make you happy in the next some minutes to see some impressions directly from the construction site. I will give you a rough presentation of the project itself, an overview for the existing system, for the existing slab track, what is there already, and for the new slab track. Of course, some words of the construction process itself, the resources, what we used in the project, and the construction technologies. The ÖBB Tauern Tunnel is located between the railway stations of Salzburg and Villach, in more details between Böckstein, the railway station Böckstein in the north, and Malnitz in the south of the tunnel. The Tauern Tunnel itself was completed around 120 years ago already, in 7.5 years, and had originally a length of 8,550 meters. Roughly 20 years ago, there was an optimization from the route in the railway station Böckstein, and because of this optimization and new position of the tracks, the tunnel got a bit shorter and has now a length of 8,371 meters. In the tunnel, there are some issues especially in the portals, water could enter into the tunnel. Especially in the portals, that was the problem that in the cold winter time, ice formations were formed. And even inside in the tunnel, the water made many issues. It created high humidity inside of the tunnel, and of course, this high humidity led into a lot of corrosion, and the fastening systems got rusted. Of course, the water was neither good for the whole infrastructure inside of the tunnel. And because of that, the ÖBB, our client, decided to make an extensive reinvestment, starting with the tunnel construction. The track itself was redesigned and renovated. Energy technologies, signals, telecommunication, and even the overhead line too. You see a picture from the existing tunnel, how the tunnel looked like before the works were executed. Itself, the project was divided in 2 phases. The first phase happened already. It was starting in November last year, finished it in summer this year, and the second phase is gonna be in the year 2027. In the existing tunnel, you can see the tunnel vault. The tunnel vault is done with natural brick stones, with natural stones. You can see already the existing slab track. The existing slab track was installed in the years 1992 and in the years 2004. Under the slab track, you can see the base channel, the drainage channel, and on the side, the cableways. The new tunnel should look like that, and it does. There were heavy measurements on the tunnel vault. You can see not anymore the bricks. It was shotcreted. A new ceiling conductor rail, illuminated handrail, and the work what we executed, the new superstructure in 1/4 of the tunnel. As I mentioned already, you can see here an overview of the tunnel itself. Here you can see the track 1, you can see the track 2. The track 1 was renovated in the year 2004. Before existed on both tracks, on both lines existed the ballast track. In the year 2004 they installed the ÖBB POR plate system, slab track. Even in 2004, they did like 1 kilometer around the northern portal and 500 meters in the middle of the tunnel. And 12 years before, in the year 1992, they did also the plate system from ÖBB POR, slab track system, and a single sleeper system, also by ÖBB POR, the single sleeper system with a roughly 4.2 kilometers. And exactly this red area was the heart of our construction site. This single sleeper slab track system we had to change. We did not change only the slab track system over the 4.2 kilometers. Additionally, in the remaining 3/4 of the tunnel, so let's say here this part in the north, the whole track 1 and the part in the south, we changed the rails, and we replaced the rails, and we also replaced the supporting points. That means the supporting points, the screws, and the fastening systems. We worked in a time model continuously 24/7. Our works were starting this year in February and lasted until May. Just to get a feeling for the dimensions, what we were confronted with, we had to change 40,000 rail support points. That means like 80,000 threshold screws and 450 tons just of fastening material. Not included rails, not included any other materials, 450 tons of fastening materials. Now the system overview. As I mentioned already, there is a single sleeper system inside of these 4.2 kilometers, built in 1992. The single sleeper system is in rubber boots, rubber shoes, and is grouted with a 4 under the sleeper in the part of the rubber boots, is grouted with a 4 centimeter thick grouting concrete, and underneath this grouting concrete a 14 centimeter thick layer of reinforced sub-base concrete. From the fastening system, there is a VW rail fastenings, and they are installed on the single sleepers. I brought some pictures directly from the construction site. You can see here the old single sleeper system. So now you can see the reason why we had to change this slab track. The reason was that the old sleepers, the single sleepers, got already cracked, quite many of them. I brought some pictures. And we decided to install, instead of the single sleeper system, the Raider 2000 sleeper system with the system what we could hear already yesterday in the presentation from Rail 1. I additionally brought a picture of the design. You can see that we had a depth of 52 centimeters. Under these 52 centimeters, there we find a solid base, a rock base or a concrete base, hard base. And we had a width of 2.5 meters. Let's go to the construction phase. That was the time schedule, a time distance diagram, what we got from our client ÖBB in the tendering phase. The construction phase itself, don't worry, you will not be able to read it, but don't worry, I explain it, is divided into mainly three big phases. The first phase starting in middle of November last year until the end of January this year. In these months, there took place the civil works. So the whole tunnel vault was renewed. In the month February, we started with our superstructure. We started to build the new slab tracks, change the sleeper and the supporting points. That was planned from 1st of February until the beginning of April. And thirdly, in the last phase, there were then all the rest of the tunneling equipment installed. Out of the first time distance diagram, of course, during the construction phase, it becomes more detailed and more detailed, became quite long already. I show you some details out of it. We, as a construction company, did it in our mother tongue, in German, but I will explain you the working steps in detail. We had to do some cleaning work. We started in the south with doing some cleaning work of the existing tunnel. And we had already to do the taking out the old slab track. Taking out the old slab track, we removed it as fast as possible. We decided to do it with 30 meters track panels and with our railway excavator, not excavator, crane, sorry. We removed these 30 meters track panels and loaded them with the crane on flat wagons what were parked on the neighbor track. These track panels we moved then out from the tunnel and then brought it for disposal. That worked quite well, quite fast. Of course, the remaining slab track, the concrete and the rubber boots you can see in these pictures. The rubber boots then we also put out with the excavators and then could clean the surface. Next to taking out just the track panels, We also started parallel already to change the rails and change the fastening systems. I will not go into detail, but here you can see all the parts, what we had to change, starting with the rails and changing all the fastening systems of the 12 kilometers where we did not change the slab track. That was the tunnel, what we found. You can see now why I said that there were quite impressive works to do to get rid of the water inside of the tunnel. There were heavy contaminations inside of the tunnel because of 120-year-old tunnel vault. Of course, you can imagine that all this water and heavy contamination is not good for the fastening system, not good for the infrastructure inside. And because of that, the tunnel had to be renovated and we had to change the fastenings and the rails. What happened because of all this water? We found screws like that. So mechanically losing these screws was definitely not funny. And we even had broken materials, a lot of broken materials inside of the tunnel. When we tried to attempt to open the screws had, of course, looked like that. So how to get them out? We were really lucky that ÖBB is really experienced in that already. Over the last years, they even designed and they developed materials and special tools to get out these screws. So in cooperation with ÖBB, thank you very much for that, we could also build a drilling machine like this one. We built 2 drilling machines and also invested in many special tools to get out all the screws. I will not go more deeper into details how we got out the screws. Maybe in the next coffee break or in lunch break we can talk about it. But it worked quite well. The next important step was to take out the old concrete. Taking out the old concrete of the slab track, I remember the words what Rail 1 said yesterday, use a lot of power, use a lot of energy as much as you can. We tried to do that, and after some days it looked like that. So you can see reinforcement concrete. We loaded it with excavators on tipping wagons and transported it out of the tunnel. As I mentioned before, it was planned to come to a hard bottom, to stone or to concrete. What we found was the old ballast from the ballast track, what was there before the year 1992. So of course, on this underground, we could not place the new slab track. So we had to dig out like 3,500 cubic meters of old ballast and remove it from there and transport it out with the tipping wagons on the neighbor track. That was then the cleaned surface of the underground. Here you can see it really good. It looks like on the moon. And it was prepared to concrete and to put a layer of concrete. We had other challenges and problems during this construction because the old cable channel, what was already more than 30 or 40 years old, got broken too. We could realize and see that already in the year 1992, they had to fix it there. So this we had even to remove and change. And also the drainage channel in the middle of the tunnel was done with natural stones, with rocks. Of course, they had different sizes, these rocks. You could see it here, you could see here. Of course, these rocks were in the concrete of the old slab track integrated. And so we had even to cut the rocks that the drainage channel does not break down completely to reach the 2.5 meters of space what we needed for the new slab track. Concreting So when we reached this point, everything worked in plan. From this point onwards, everything worked in plan. The old system was deinstalled. We could concrete the new leveling concrete, the base layer. We did it with conventional mixer trucks, going in with wagons and fill in the concrete. That was the correct concrete base layer. You could see that in the design it was planned that we have here a good base. We had to fill in all this concrete, and of course we also had to fix some parts of the base channel. The next step was to put in the sleepers. The sleepers we put there conventional with our excavators. That was working quite smoothly. Put in there the reinforcement. Then installing the lifting and alignment system. For the lifting and alignment system, we also had to be a bit smarter. We could not install it on both sides. So usually you can install it on this side and on this side, and just with putting pressure on the bars to bring it in the correct position. The lifting work was easily done with our spindles, and we had to develop the alignment system so that we can just fix it on the rails from the neighbor track and on the rail from the new track, and do it with the tensioning parts, that we can tension it and that we can also press it to the correct level. Afterwards, we went for concreting. For doing the concreting, we made some examples. We made some tests. You can see here that we formed these boxes with a piece of sleeper, with a plexiglass, and we could also see then in the video, when we fill in the concrete, how it reacts underneath the plexiglass. Worked quite well. We unpacked these boxes. First results, we were not happy, definitely not. You could see that air was on the surface and water was on the surface. And finally, we became better and better, and we found our correct recipe. We put in the concrete with a paver. On the paver were mixers installed, what could mix the concrete once again. And we put it efficiently on the construction site. You can see the concrete flowing and coming underneath the sleeper. Afterwards, doing the concrete surface, conventional, bringing on the applicated the evaporation protection layer, and we had our new slab track installed. The last steps have been welding of the rails, transporting out of the tunnel the old rails, and the project was done. Thank you very much.
Thank you, Thomas. I think this is the beginning of a lot of similar projects, because time is continuing. Then the next session is static and dynamic investigation of mass spring systems in Chile, from Elisabetta Pistone. Thank you.
Good morning, everybody. My name is Elisabetta Pistone, and as correctly pointed out, I will present today a project actually, on static and dynamic investigation of mass spring system in Chile. a project and a work that I carried out with my colleague Henno Töll, which can be here. I will briefly go through an introduction of the project. I will mainly concentrate on vibration studies, although I will briefly talk about static and dynamic design and the construction and manufacturing as they have influences on vibration studies. And I will finally a little bit elongate on site measurement, which is something we have not been hearing so much in this conference, in this forum. Before that, I will spend a few words on VCE. Although many of you know us and we have a long-standing collaboration and successful with some of you, it is, I think, worth mentioning that we are an engineering office with headquarters in Vienna, although we have branch offices also abroad, mainly depending upon request of projects, I would say. We covered pretty much all the fields in engineering, so spanning from bridge design, track design, traffic, noise and vibration, this is my department, life cycle. In the last years, we also had the development of BIM, and research and development is always the key. It was founded around '86. We have more than 350 employees, experts, as I before explained, in different fields. And our project covers pretty much the globe, I would say. Of course, Europe, Germany, Austria, Italy, geographic Europe as UK. But we also have, like yesterday, my colleague explained with POR as well, some project in Qatar, we have in India, and here we go in South America. Why I chose this project? This, I think, it's a successful example of collaboration, I would explain, among different interfaces of what track design is. The project took place over different phases. It is a construction of a metro line, of the metro with different lines. And we were involved in different stages for different type of purposes. So always related mainly to noise and vibration, but it was not only the theoretical computation, I would say, also we had site measurement, mock-up, and test when the system was already positioned in place. From, let's say, a theoretical standpoint, when it comes to acoustic and vibration, this should be the, let's say, the path to follow. So, although it seems either a series or for some expect a parallel system, it is a loop system, which means that each block at the end of the process had always to answer a question, yes or no. If yes is answered, you could proceed to the next phase, which maybe leads to also another interface. And if no is answered, then you have to go back. Go back means to optimize the system, to change something, to revise what you have done. So for instance, in the case of noise and vibration, if you have definition of mitigation system, you have to calculate natural frequencies, insertion losses, preliminary cross-section. If this is compatible with main work civil construction, you could proceed to the track design. For instance, in the case of calculation of preliminary reinforcement, concrete, and so on. And if adaptation of mitigation system is required, then you have to go back and you readapt and optimize your system. Otherwise, you could proceed. This is pretty classic. Seems easy, not always is so smooth. As far as the prediction, vibration prediction is concerned, the main key point to answer is always the calculation of emissions, which comes from a contribution of different aspects. So you have the train emission, insertion losses, soil, of course, propagation through soil, the coupling with the building, as well the building transmission itself, and a safety factor always to include uncertainty. So if you look at the picture, you have a source, a train passing, for instance, in this case, in a tunnel, presuming a tunnel, so we have a certain depth, which will have its own insertion losses depending on the system you are considered. The vibration, of course, will propagate through the soil, which has an influence until it reaches a building. Of course, when you analyze a line, on the old map, you cannot take every single building along the line. You have to spot what is called sensitive receiver. In this case, we are following the FDA, which means receiver that can, buildings, I would say, that could be representative for a category. So it could be depending upon usage, residential rather than schools, and also about importance and vicinity with the rail. Then, of course, the vibration propagation will reach one of the sensitive receivers. So let's say the building will transmit through the fundament, depending on which they are, and then it will, after this, propagate through the building itself, so depending on the stories with the transfer spectra. So this was the image, of course, according to the process of FTA is very, very similar. So you have to determine, as I was saying, the sensitive receiver, measure the vibration through the excitation source. So the train in this case, which will go through the soil itself to the building until you can calculate and predict effectively the ground-borne noise and select if you need mitigation measures. Could be yes, could be no. If yes, of course, into the detail, which one are they? In our case, our client was designed. The reason why, yes, we were involved at the very early stage, so we could, let's say, assess the system that they have designed and that they wanted to put in place, and then at a later stage that we could test the system put in place. They actually chose 4 different systems. One was sections without any mitigation measure according to their analysis. One system was with elastic rail, so elastic soil, and 2 mass spring systems. The same exact mass system, the only difference was the thickness in the elastic mat. In one case was 40 millimeters and the other case was 50 millimeters. Why? Because they had constraint upon the frequency. We can discuss about optimization in a different stage maybe, but these were the requests. So one was 15 hertz and the other was a little bit lower, so 13 hertz. So this is pretty much the mass spring system, and the difference was in the thickness of the mass that they adopted. We also calculated and we performed an analytical study to determine the dynamic stiffness for the bearing and the effective dynamic masses. And of course, we did also static calculation with the collaboration with another department to calculate the reinforcement quantity and the verification according to different states. I'm not going to dilungate a lot because this was just for us an input according to, for the noise and vibration part. After that, we were finally requested to test, and we tested both in a part of the mock-up test, so before putting into place and operation. I'm not going to talk about this stage for sake of time. I rather concentrate on the measurement when the system was put in place to detect the natural frequencies of both loaded and unloading system. And of course, we had also to consider the contribution of soil because we were able to test it. Not always this is possible. Sometimes you have to simulate this propagation. In our case, since we were able to test it, we could directly compute it. So there were mainly 13 sections. The first 3 sections were system with elastic soil, and then from section 5 to section 10 was the mass spring system with the 40 millimeter with 15 hertz resonance frequencies, and the second was from 11 to 13 section, so 3 more sections, 50 millimeter map for the mass spring system with, as explained before, of course, a shifted frequency in the lower domain around 13 hertz. So this was what the theory was computed and the mock-up test told us. And when we finally tested in reality, we could, as I mentioned, also take into account the ground correction. So from the first step is to compute the insertion loss. So the insertion loss is always basically a measure of the performance of a system that you are putting into place, in this case a mitigation measure, in comparison with a reference system. If you also want to add the ground correction, the right thing to do is, of course, compute the transfer function, which is you are performing a test on a system, so it's always an output of an input. You are impacting, for instance, and you're measuring something. So you have an input, you have an output. So the first thing is to calculate the transfer function of your reference system meaning a system without mitigation measures. So the pure, the basis, the baseline, I would say. And you subtract from these what is the contribution of the ground propagation. So the same exact test, but rather than impacting, for instance, on the, well, without the instance, without impacting on the ray, you impact directly on the soil. The subtraction of the two will give you the transfer function corrected for the reference system. If you do the same exact procedure from the mass spring system, you can imagine that you will see the contribution of what your mitigation measure is, and the difference among the two, from a mathematical standpoint, will give you your ground correction, which you can add to your analysis. The same thing you can do on the track with elastic soil. Difference among the two procedure is location point for impacts, but the concept itself is the same. In our case, we did 3 types of campaigns in situ. One was for unloaded system, so system without not impact, because you can have either static or dynamic impact. So static impact are hammer, for instance, and dynamic is the train passing itself. So first step was testing the unloaded system. Why? To detect the natural frequencies that we have computed earlier from a theoretical standpoint. And there was pretty much a very good agreement, especially when it comes to the mass spring system. So you could see here the location of the impact and the receiver from section and plan, and the result of the natural frequency. So natural frequency was actually proven correct. We did the same, but then with the static loaded system, meaning we carried out 15 to 20 impacts with the hammer. This is pretty much what the norm says. Why? Because you have to average, of course, in case you have outlier, to have a statistical population increased. Here is the location both of the receiver and the impact, both in the cross-section and in the plan section, and the computation of the insertion loss is what comes out from the loaded system, both for the elastic soil and from the mass spring system. The red line here was one of the requirements of our client, although from our calculation was not exactly correct, so don't be deceived by this line, because actually the agreement among the curve was pretty high, I mean, when you average the result. And the same exact thing was doing the train passing. So we recorded train passing. Velocity were around always 50 to 80 kilometers per hour. And also in this case, we could compute the insertion losses, both in the case of elastic support and the mass spring system. Also here we had a pretty good agreement. Of course, in this case, the train is passing, so the sensitive receiver are actually 5 meters apart by norm from the tracks. And also in this case, we're good. So coming back to the original question, when you have your loops, being involved in an early stage, allowed us to improve their design and give feedback and optimize what they originally designed in some cases. So we also did, I added this slide because yesterday we had a very nice presentation about rail roughness. We also did a short campaign on rail roughness. In our case, we had some trouble while measuring, so we had a pretty good agreement until 50 millimeter, I would say. Then after this, we had pretty much problems, I would say. But at least the vibration due to the rolling wheel, I would say from the statistical data was comparable and reliable. So the outcome of the whole project is that generally vibration engineering and track construction planning are, of course, well, not of course, but generally carried out by different planners, but an early involvement allows an optimization of the system. And interfaces, in this case, must be defined as a processive that is iterative, also not theoretically, but also practically. And this is what happened in our project, where we both had the mock-up test and the test measurement. Although the results are not always perfect, definitely it was demonstrated that all the basic requirements were met. So it was considered a successful example from our side. And with this, I thank you for your attention. And if you have any question, I'll be happy to answer.
Thank you very much, Elisabetta. An important theme, even in ballasted track, you have today to prevent from vibrations, as we learned in Switzerland. And now we have the Q&A session. Where are questions?
Yes, good morning. My name is Rick Monteban from Edlon Cedra. I have a question for Swietelsky. Were specific measures taken for the screws and the fastenings to prevent further corrosion or maybe easy exchange for rail pads operations, etc.?
Thank you for the question. In our case, all the material was delivered by the client. We used special material, what I guess we use all over already now. So they have a special, how do you call it in English? I have to, maybe somebody can help me with, how is this word? Auf Deutsch ist verzinkt. What is the correct?
Galvanized.
Okay, thank you very much. So as far as I know, it's galvanized, yes. Yes, the new material.
Also the use of grease maybe in the screw and the dowels, perhaps?
Also the screws itself, yes.
Yeah, but I mean also in to use grease, the dowels? To prevent
the dowels are plastic dowels. So between the screws and the dowels we had the specific oil.
Okay. It's for you.
I'm Mario Galova from Bulgarian Railway Infrastructure. In Bulgaria, you use same construction of the slab track, and we have a big problem in one tunnel because the train derailed. Have you a technology, specific technology, to repairing the track when the train is going in the windows? Because I like to understand it's made without any moving the train. Thank you.
Yes, that's true. That's true. We had a total track closure. So on the neighbor track, there was not allowed that any trains are driving. Well, I think the fastest system to get it out is definitely if you have a train with tipping wagons or with any special wagons on the neighbor track. I think you also have to do the same method, demolishing, let's say, the track itself as fast as possible. Maybe for the demolishing you have time, even if on the neighbor track the train is driving. But of course then use the small slot to unload it, to upload it as fast as possible and transport it out of the rails. Mechanically, maybe it's possible if you use like milling machines. Maybe that is also a fast way. We did not use it in this case because 4.2 kilometers is not a too long and too big construction site, so we did it conventionally.
Good morning. I have a question for the last presentation. Richard Stock, Blaser and Teurer. You showed rail roughness results. So I'm not sure, did you do was it just like the natural roughness that occurred there, or was there some grinding done, or?
There was a little bit of grinding done, but mainly it was just the pure roughness of the system. Yes.
And you were focusing on wavelengths 40 millimeter and above.
Yes.
Okay,
because it was actually below, so the results below were in agreement, and then we also performed the above one, and then where we don't have a good agreement of the results, basically.
Okay, thank you.
Take over.
I have a question to Mr. Hofmann from the Brenner-based tunnel. I know that so many kilometers of tunnel is quite difficult to build. Have you ever faced a situation or problems with the drilling or in the tunnel, like probably in other tunnels, they have big problems when the machinery gets stuck or something like this? Was the geological situation always as expected, or did you also have sometimes a little bit worries that you get stuck or something is going in the wrong direction?
Yeah, thanks. You know, in tunneling, it's not the usual case that it's like expected. So we have some special situations. Quite interesting was the comparison of the tunnel boring machines. We had an exploratory tunnel, an open machine, which had several overbreaks. And now in the main tunnels, we have closed machines which perform very well. We have no stuck of the machines. Very interesting and demanding was the so-called Hochstegenzone, which was actually a construction lot with Swietelsky 2 years ago, where a large water ingress took place with something like 70 liters per second. It was a cast-like zone. It was very demanding and very good cooperation with Swietelsky to inject the rock mass and to get it a safe excavation from that. So that was on the Austrian side one of the most demanding situation. And in Italy, there's the so-called peri-Adriatic NAT. So it's the transition from the Alps, from the European plate to the African plate, especially. And this was a very big damage zone. And that was also very demanding for a tunneling aspect.
Other questions? You have also the possibility to take your questions outside on the booth and by the coffee break. So I would close this session here. Thank you for the very interesting presentations and other applause.